Our members are Momal, Sanjay, Kasoon, Dan, and Mehdi. Our presentation basically divide into 4 parts: introduction, modernizing the ConvNet, evaluating ConvNext, and conclusion. So modernizing the ConvNet breaks down into two parts: macro design and micro design, and evaluating ConvNext break down into 2 parts on ImageNet and on downstream tasks. So the paper tried to bring the idea CNNs can do as well as transformers. The question arises is how. The answer is modernizing the ConvNet using a SWIN as a motivation. So here they propose a new architecture called ConvNext, which outperforms SWIN on detection, classification, and segmentation. So now we talk about evolution of vision architectures. So we know 1998 LeNet. In 2012, revolutionary AlexNet, which followed by another great papers based on convolutions. This is called CNN Zeta. So then in 2020, VIT came, followed by another transformer-based papers. Then the transformer era started. So here is an attempt to revive convolution-based architectures, which is based on ResNet, influenced by SWIN. They make a new purely convolution-based architecture called ConvNext, which outperform all the remaining architectures. So hierarchy of SWIN versus CNNs. So we know vanilla VIT failed in common vision tasks such as semantic segmentation, object detection. Then hierarchical transformer SWIN introduced as a general purpose backbone architecture, which perform well against the shortcomings of VIT. SWIN was credited for transformers' intrinsic properties for the success. So actually, when we look at the convolution architectures, we can see we have spatial, that means height and width, and the channels. So along the way, we can see that the spatial dimensions reduce and the channels increases. So when we look at the SWIN block, we can see the spatial height and width again reduce while channels are increasing. So paper indirectly trying to say this is a property that is already existent in CNNs, but for the success of SWINs, it is entirely credited for interesting properties of transformers. So here, what they're trying to do in this paper is modernizing the ConvNet. So they take ResNet and they do changes to the whole architecture based on SWIN as a SWIN transformer. You know, it is influenced. And then we have a micro design. They check network level changes, which Mehdi is going to talk about. Previous one, Momal is going to talk about. And then we have some training techniques, which they change the epochs from 90 to 300. They're changing the optimization into ADAM-W. And especially, and most importantly, they have 3 new augmentation techniques that was not published at that time. And these are state-of-the-art. And then they have a latest state-of-the-art regularization methods. So altogether, combining these 3, we have ConvNext. So Momal is going to talk about the rest.
By the way, this was very nice. What an improvement you made compared to Friday. Very good job.
Thank you, Professor.
Awesome. I believe I'm audible. Okay. So I'm going to talk about modernizing ConvNets. So exactly what they are doing is that they are taking a base model of ResNet 50, and they're going to use a SWIN tiny architecture as motivation to introduce changes into a ResNet 50 architecture. So initially they start off with the ResNet 50 architecture. They make a series of changes, which is classified into macro design changes and micro design changes. And they introduce a new architecture called ConvNext. which results in an accuracy increase of almost 4%, which we can see here. The original ResNet, the vanilla ResNet 50 had 78.6% accuracy on image classification on ImageNet dataset, and the final ConvNext model will have almost 82%. They managed to do all these changes while keeping the flops under 4.5 gigs. And this final architecture was able to outperform SWIN, which is obtaining an 81.3% on image classification task. I will cover the macro design changes, which are 5 in number, and we will go over all of them in detail in the upcoming slides. So the first change is changing the stage compute ratio, which is very simple. If you look at the number of blocks in each stage of ResNet 50 architecture, we see there are 3 convolutional blocks, then 4, then 6, and 3. So the stage compute ratio is 3, 4, 6, 3 for ResNet 50. If you look at a SWIN tiny block, we see that the number of SWIN transformer blocks is 2 in first stage, followed by 2, 6, and 2, which can be simplified or expressed in lowest form as 1131. So the author took this idea and they changed the stage compute ratio to 1131 as is done in SWIN tiny for their ResNet architecture. So the number of blocks in first stage is 3, 3, 9, and 3. This change resulted in an improvement of 0.6% over vanilla ResNet. So previous architecture had 78.8% accuracy, but this change improved the accuracy by 0.6%, and we have a 79.4% accuracy. So from this point onwards, we are going to use this stage compute ratio. The second change that the authors made to the ResNet architecture was to the stem. Stem is nothing but the first layer of a neural network architecture. So we see that in ResNet architecture, the input stem or the first layer is a 7x7 convolutional layer with stride size of 2. Whereas we know in a SWIN tiny architecture, the first layer is patch-ifying, in which we divide the input image into 4x4 sized non-overlapping patches. The thing to notice here is that this receptive field or the patch size is 7x7 in ResNet and 4x4 in SWIN tiny. And the second difference is that these patches are overlapping. That means the filter is attending to to central location multiple times as compared to the border of the image. And the stride size is 4 for SWIN tiny. That means these patches are non-overlapping. So what change exactly did the authors made? They changed the stem cell to 4x4 convolutional layer from a 7x7, and they changed the stride size to 4. That means now the kernels will not overlap. This change resulted in an improvement of 0.1% over the previous accuracy. So now we previously had 79.4, but now we were able to get a 79.5% accuracy using a patchified stem. So from this point onwards, we are going to use a patchified stem. Before diving into the third change that the authors made, we need to understand what is depthwise convolution. So if you look at a normal convolution, we place a filter at one location in the input image, we convolve it, and we get 1 pixel in the output feature map. But if you split your filter channel-wise and you split your input image too, you get something called depthwise convolution. So assume each slab here is a channel in the input image. So R is 1 channel, G is 1, and B is 1 channel. So what you exactly do is that you split your input image into 3 channels. You repeat the same process for your filter as well. You convolve each channel of the input image with the respective channel of filter, and you get 1 channel for the filter for the output feature map. In the end, we concatenate all the 3 feature maps, and thus we get our depthwise convolved feature map. One thing that I want you to notice here is that the number of parameters in depthwise convolution tends to be less than the normal convolution, because in order to get a feature map like this, we will need 3 filters like this to if we are using normal convolution. But with depthwise convolution, we need just 1 filter like this to obtain an output feature map of this dimension. So the main idea is that depthwise convolution tends to have fewer parameters as compared to normal convolution. But the question arises, why depthwise convolution? So the idea is very simple. Depthwise convolution is quite similar to self-attention. How exactly? Well, the channel-wise filter application that we do in depth-wise convolution is kind of similar to the weighted sum operation that is done in the self-attention mechanism. So if you look at how self-attention works, we divide an input image into tokens, we pass it through a self-attention layer, and we get a 9x9 attention map for the tokens and 9 value vectors for each token. We multiply this attention map with the value token, and we get an attention encoding for all the tokens in our input image. Now, if you look at a depth-wise convolution, you have a kernel and you have an input feature map, and their channels have to be same. Each kernel is convolved with each feature map, and we get an output feature map for each channel, which are finally concatenated. Now, you can think of these two as similar because the way we are convolving an attention map or multiplying an attention map with value metrics is kind of similar to how we are multiplying each channel of kernel in the depth-wise convolution to each channel of the feature map. Particularly, we can think of value metrics here similar to our feature map, and the kernel vector, which are weights, similar to our attention map. So based on this similarity, what they did exactly was they simply changed the normal convolution to all depth-wise convolutional layers in all the blocks of the ResNet architecture. So the small d that I've appended here actually says that now this is not normal, but a depth-wise convolution. But this change dropped the accuracy by 1.2% and flops were improved by 2 gigs. Why exactly? Well, I mentioned that earlier, that depth-wise convolution tends to have less parameters. That's why the accuracy started off by 79.5. But when I changed the convolution to depth-wise convolution, the accuracy dropped to a 78.3. So to combat this effect, what they did was that they increased the size of the dimension, the feature dimension in the stem cell, and they increased the number of channels in the subsequent convolutional blocks. Like this exactly. So the blue that is showed here, the changes that are shown in blue are the changes from the previous stages, and the changes shown in red are the changes which were done after changing the filter dimension and the number of filters at each stage. So what they did exactly to improve accuracy drop, which happened after adding the depth-wise convolution, was that they changed the filter dimension in the stem cell from 64 to 96, and they increased the number of filters in each block with a ratio of 2. What this did was that it increased the accuracy by 2.2%. So now we see that the change, the decrease that happened by introducing depth-wise convolution was overcome by increasing the width or the number of input, the dimension of feature map. And we also see that because we are adding more parameters, we are increasing the number of filters, the flops are also increasing from 2.4 to 5.3. One more thing that they observed, which is the fourth change, that in multi-layer perceptron of a SWIN transformer block, they saw that the hidden dimension is kind of increased. It's multiplied by 4. When they observed a simple ResNext block, they saw that this pattern is kind of inverted. And originally in a ResNext block, the dimension is first decreased, then we apply the depth-wise convolution, and then the dimension is increased. They wanted to adopt an architecture like this, so they inverted the bottleneck. And what they exactly did was that they used this inverted bottleneck architecture by shuffling the layers inside a block. So first, they are placing a 1x1 convolutional layer to increase the dimension. Then they're applying the same depth-wise convolution on this increased dimension and then scaling it down again. And the dimension ratio is multiplied by 4, which is a pattern also observed in SWIN architecture. So after inverting the bottleneck, I computed these dimensions and I've cross-checked them with the code in the repo as well. So they are shown here in the red. So this is how the blocks will look like after applying the inverting bottleneck idea. And the improvement that they got after using this fancy fancy technique wasn't much. Their accuracy improved by just 0.1%. So they started off by 80.5, but they got an 80.6% after inverting the bottleneck. I'll be talking about the last but not the least change, which is the larger kernel sizes. If you look at a ResNet architecture, you can see that the convolutional kernel size is 3 by 3 in all the convolutional blocks. But if we look at a SWIN tiny architecture's self-attention block, we know that in SWIN tiny architecture, the attention is computed in local windows of 7 by 7. That means the receptive field is of 7 by 7 in self-attention blocks of SWIN tiny, whereas here the receptive field is of 3 by 3. Well, the authors thought that why not to increase the size of the receptive field in all the convolutional blocks and see if it improves the accuracy. So what they exactly did was that they replaced the 3 by 3 convolutional kernel size to 7 by 7, and accuracy unfortunately did not improve. They did not just try 7 by 7, but they tried a whole bunch of different kernel sizes like 5, 7, 9, and 11. But they couldn't see any improvement accuracy which they observed after the fourth or final change. So they used a kernel size of 7 by 7 for all the kernel filters through all the convolutional blocks. And that's the end of my part. And I'll hand it over to Mehdi to talk about the micro design changes.
Okay, can you see my screen? I'm going to go through on the micro design changes of the ConvNext. The first one is replacing RELU with GELU. The second one is fewer activation functions. Third one is the fewer normalization layers. Fourth is substituting batch normalization with layer normalization. And the last one is separating the downsampling layers. The first changes, the micro changes that they've done on the layer-wise convolution, they replaced the RELU with GELU. RELU is the rectified linear unit, and GELU is Gaussian error linear unit. So as you see here, if we compare the RELU with GELU, we see that the GELU is actually a smooth version of the RELU. And this GELU actually used in the BERT, GPT-2, and all the VITs. So they adopted this activation function from these well-known transformers to improve their accuracy. So as you see here, when they use the GELU, with RELU, change the RELU to GELU, they didn't show any accuracy boost in the evaluation, and as you see, they didn't see any accuracy, 80.6. So the next change is that they use fewer activation functions. As you see in the standard ResNet block, they use the activation function between each convolutional layers. And in the ConvNext, they just used one activation function between the second layer and third layer. The improvement of this change actually was from 80.6 to 81.3. So it was 0.7% accuracy boost in the performance. But the flops didn't change because it doesn't have any effect on the number of parameters. So the third change was the fewer normalization layers. Which they used in the standard ResNet block, they used batch normalization between each layers of the convolution. But in the ConvNext, they just use one layer normalization between the first layer of convolution and the second layer of convolution. This shows 0.1% accuracy boost in the evaluation metric. So the fourth change that they did was substituting the batch normalization with layer normalization. As you see, the batch normalization is calculating the mean of each batch. As you see, it's I from 1 to M, which is the batch part of the feature map. And they compute the variance of the mini batch that they have in the feature map, and they use this formula to normalize each batch in the feature map. But as you see in the layer norm, we have a different dimension of the computation. So as you see, for each mean of they didn't use batches for computing the mean, but they used the other dimension of the feature map to compute the mean. And they did exactly the same thing for the variance, and they compute they normalize the batch the feature map with this formula. And as you see for the visualization of it, the feature map of the batch normalization is like this, and they normalize the feature map by selecting this part of the feature map. As you see, the C is the channels, N is the batches, and H and W is the widths and heights. And as you see here, the layer normalization actually did do that in the different dimension of the feature map. So for that improvement on the by doing this is actually 0.1% by changing batch normalization to layer normalization, and the flops did not change because it doesn't have any impact on the number of parameters. So the final changes that they did in the ConvNext, they separated downsampling layers. As you see here, for the skip connection in the ResNet, standard ResNet, they have something like this that they called residual blocks. So as you see here, they have the ResNet block that is coming here, and the residual block that is trying to escape the connection, and they have two conv layer here, which have in here they have 3x3 kernel with stride of 2, and in here the final layer they have 1x1 kernel with stride of 2. But they changed this paradigm by if we have the ConvNext block here, they just use a layer normalization, and they use a convolutional layer in the final layer, and the convolutional layer was 2x2 kernel with a stride of 2. Interestingly, this modification leads to the diverged training. So when they did this thing, the training diverged. But they add the normalization layer whenever they actually did change the resolution of the feature map. So this helped to stabilize the training, and this improved the accuracy by 0.5%, and the accuracy gets to 82.0. So final ConvNet block actually consists of macro design changes and micro design changes, and ConvNext actually has the similar flops as SWIN transformers, which is 4.5 gigaflops. No special modules. They didn't use any specialized modules like SWIN transformer, which is like shifted window attention or relative position bias. And they only use convolutional layers. As you see here, the SWIN transformer blocks is shown here, and the standard ResNet block is like this, and the ConvNext block is like this. They actually adopted many things from the SWIN transformers, and they try to stay in the same ballpark of the ResNet block. And all design choices discussed so far are adopted from vision transformers, so they didn't have any of their own ideas. They just wanted to make the ConvNext as similar as possible to SWIN transformers, and these design changes are not novel. Even in the ConvNet literature. So all of these design changes was discussed before on the ConvNet literature, but separately, not collectively. And what they did in this paper, they just combined all of these design changes, and they saw the improvement. And as you see here, for the summarization of this part, they started with the ResNet 50 model, which is the baseline. They did some macro changes, which improved the accuracy from 78.82 to 80.47. And then they did the micro changes which improved the accuracy further from 80.57 to 81.97. And this actually outperforms the SWIN tiny transformers, with which the accuracy was 81.3. And I will hand it to Sanjay for the continuation of this presentation.
I hope I'm audible. Today I'll be talking about the evaluation of ConvNext on the ImageNet. In the following slides, I'll be talking about the networks that have been chosen for evaluation. So the authors have chosen different variants of ConvNext. That is the ConvNext Tiny, ConvNext Small, ConvNext Baseline, ConvNext Large, and ConvNext XL. So all of these variants basically vary only by the number of channels in these successive layers and the number of blocks in it. In order to compare the results of ConvNext, they have also chosen two different architectures, that is the ConvNet architectures and the transformer architectures. So in the next slide, I'll be talking about the training settings that has been utilized. So the authors have considered two different training settings. The first one being the ImageNet 1K, that is the model will be trained from the scratch. And the following are the parameters that have been used. The first one being the Adam W optimizer, which was already mentioned by Mehdi. And coming to training epochs, they have trained the model for 300 epochs with a warm-up of 20. Going ahead, they also chose different regularizations, that is the stochastic depth and label smoothing. Stochastic, this is something like our dropout, wherein the layers are dropped for each of mini batch, as compared to the dropout in our networks wherein we drop the neurons. And talking about the data augmentation, they've utilized multiple data augmentation schemes like mixup, randog, and cutmix. Mixup looks something like this. Let's say we have an image of a dog and a cat, and after applying the data augmentation, we'll be having something like this, which is a combination of both cat and a dog. And the other augmentation would be cutmix, and this is what it looks like. They randomly crop a portion of the image from the actual image and paste it with a different class image in that. And the labels look something like this, that is 60% of dog and 40% of cat. They also have utilized another regularization method, that is exponential mean average and the layer scaling. We'll not be talking about much about that because that is not the scope of our paper. The next training scheme is the pre-training on the ImageNet 22K dataset, wherein the model was trained for 90 epochs with a warm-up of 5 epochs, and there was no exponential mean average utilized. And once the model is trained on the ImageNet 22K dataset, it will be following the same procedure as that in the ImageNet 1K dataset. In the next slides, I'll be talking about the results that we obtained after training the model on ImageNet 1K. So the author is trying to compare the results obtained with SWIN as compared to the ConvNext. And it's clearly visible that we are obtaining an improvement of 0.3 in the first case, as also visible. It is also improvement in the small variant as well as the tiny variant. Another thing that needs to be noted is that even after training the model on ImageNet 1K from scratch, the accuracy couldn't outperform the accuracy that obtained with the ConvNet architecture. And the only takeaway from this results is that the SWIN was outperformed by the ConvNext architecture, both in terms of the accuracy and throughput. And the other one was ConvNext still lags behind the ConvNet, that is efficient at V2. Moving on the next slide, I'll be talking about the results that we obtained after pre-training the model on ImageNet 22K. So here are a few of the results that we obtained with the ConvNext tiny variant. And the accuracy that is mentioned on the side of this is in comparison to the model that were trained from scratch. So it's clear that we have obtained an accuracy improvement of 0.8% as compared to the training from scratch. The same goes with the other variants. And here is the accuracy improvement. And finally, it must be noted that this time when we train the model on 22K, that is a large data set, we're able to surpass the accuracy as compared to the ConvNet architectures. So that will be the only takeaway from this slide. And yeah, So the takeaway is that we observe the scaling property of transformers in ConvNext. That is, when the transformers are trained on large data sets, it was able to get a good accuracy, and that is still being observed in the ConvNext. The other observation in the paper is that the author tried to infer the models on different hardwares. Initially, all the results that were shown in the previous slides were run on a hardware known as V100 GPU. So there, when we could see that the inference difference was slightly less as compared to the SWIN architectures, but when the models were inferred on a different architecture known as A100 GPU, we're able to see a high inference difference, that is a 47% inference improvement. So that's all from my side. I'll hand over it to Dane for isotropic ConvNext part. Thank you.
Awesome. Yeah, I'll be briefly concluding our presentation. So one of the ablation studies the authors did is they examined what happens when the features are set to the same number, that is, they don't vary throughout the pipeline. And this is the isotropic architecture. So there's no downsampling layers. And they were able to generalize this so that they can compare this to VIT. And what you see is this common theme that the authors have been showing, that the really the VIT and ConvNets are and SWINs are all on par. So next I'll go over the evaluation on some of the downstream tasks. So they ran this on COCO, that's object detection, and as you see, just that similar theme of, hey, this performs on par, if not better. So in a couple cases, there's slight improvements within 8%, but for the most part, they're really about the same and competitive. And then we see that here with segmentation tasks on 80/20K. Again, those scores are just really close, slightly better, and just that similar theme. So yes, overall, the ConvNext proposed model that competes with transformers. The authors hope the importance of convolutions is re-examined within modern vision architectures. And that's something we just want to point out here is really this paper just kind of shows you that the importance of optimization in getting improved scores, not just like complete architectural designs. So yeah, and then there's a kind of question here, which is the optimization the important part of this, or is the convolution architecture is the important part? And yeah, that's ConvNext. Thanks.